dark energy. And then, so after introduction, I'll briefly mention the kind of research I actually was doing using computer simulations, actually study the dark side of the universe. Okay, so let's just go to the first player. Okay, so the first player of the dark side, first character of the dark side is the dark matter. Okay, so how do we know, we have dark matter? And by the way, how do you actually say this dark matter? Okay, so dark matter, of course, two words. The first word is matter. Okay, is matter is not energy. Okay, so you have mass, because it's matter, and then the second, the word before the matter is dark. Okay, if I say dark, of course, it doesn't really give us any light. We cannot see the dark matter. Okay, so the first evidence of dark matter is probably from early observation of the galaxy clusters in early 20th century. Okay, so at the time they observe, okay, so the galaxy cluster on a large scale, and then they map all the galaxies in the galaxy cluster, in this case the Coma cluster, Rich cluster, and then they also detect the speed, the relative motion of those galaxies. And they find out, okay, so if we just use simple Newtonian gravity, the gravity everybody knows, okay, so like physics 101, and it turns out those velocities cannot be explained, by all the galaxy, the mass of galaxy we, have found. Okay, so we need more mass to hold all the galaxies together. If the galaxy has have those velocity, have those motions. Okay, that means we miss something. We miss some mass. Okay, so there's something must be there has mass. Okay, so the second proof, we know. Okay, so there's something we cannot observe, but we can feel the effect of gravity, is that from our own Milky Way. Okay, so this is the artistic rendering of our current understanding structure of the Milky Way. This is not an actual picture, but it's close the Milky Way should be like if we just look from from a distance. Okay, so by measuring the rotational velocity, rotational speed around the center of the galaxy, and so the rotational speed of stars or the matters around the center of the galaxy, and we have this plot is called the rotational curve of a galaxy. So in this plot, it gives you the distance from the galactic center. Okay, so for the stars in parsec is basically light years, 3.26 light years, and they give you the orbital speed in kilometer per second. So all those stars, they are orbiting around the center barge of our galaxy. Okay, so once you plot this rotational curve, you find, okay, so the rotation curve has this funny shape. Okay, and so one thing you do notice is that when you have a stars further away from the galactic center, the speed actually is not decreasing, and it's flattened also actually increased a little bit. Okay, so that's what we observe. But we have, don't forget, we have, we are not even talking about the general relativity. We're talking about the Newtonian gravity. If we just have a simple Newtonian gravity model, and then we add all the mass we have observed, all the mass of stars, the visible matter we have observed, we find, using our theoretical model, using Newtonian gravity, the rotation curve should not be like the one we observed, especially from a distance, in this case, more than, say, 10,000 parsec from the center, the rotational curve should be falling. The speed of the star orbiting the galactic center should be falling with the distance, but that's not what we observed. Okay, so we believe what we observed, the data is right, then what's wrong with the theory? The Newtonian gravity probably is fine on this scale. We don't have a black hole, we don't have extreme condition. So if we presume the Newtonian gravity is still valid on this scale, and then there must be something wrong. Okay, so either the observation is wrong, or that's not likely, or we miss something, we miss some mass there, the mass we cannot observe. Okay, so this is not just about our Milky Way. This is also the true for other galaxies. Okay, so you find the rotational curve that is derived from what we have by combining Newtonian gravity and the mass we observe. So we think, okay, somehow we missed some mass. We missed some mass in our galaxy. Those mass has gravity. Those mass we cannot observe. So one way to think about it is that, okay, so this is another picture, okay, shows what actually the Milky Way galaxy will be like if we, include the mass we don't really see, okay? So at the center, there's our galactic disk, and then there's a halo, there's a spherical halo of matter actually surrounding our galaxy. That's we call, again, so dark matter, the matter we don't know. The actual term of dark matter, it's not just come very, for a long time, but, the concept is from even early 20th century. Okay, so we have the evidence for the dark matter. Is that really the case? Because as some of you may know, okay, somebody just proposed, and we have a modified Newtonian gravity called the Mount. Okay, so Newtonian gravity is not right on the galactic scale. Is that case? Well, just from the galactic curve, well, you can think about maybe that's the case, but we have more evidence. Okay, so another evidence we have, is for a missing matter is so-called the gravitational lensing. Okay, so the idea of the gravitational lensing is from the Einstein's general relativity. I don't want to just go to the theoretical model, but basically it tells you, okay, so this gravitational lensing tells you if you have a distant galaxy, and then you have a foreground galaxy that between you, the observer, and the distant galaxy. And when the distant galaxy passing through the line of the sight connect the distant galaxy, the massive galaxy between you and the distant galaxy, the image of the galaxy will get some sudden change. Okay, so what kind of change? And so in a way, say it will get brightened. Okay, so if the galaxy just has a direct, is on the direct line between the connection, we call the massive galaxy between the distant galaxy and the observer, the lensing galaxy. If the lensing galaxy is just directly line up with the distant galaxy and then the observer, it will form a beautiful image we call Einstein ring, or even partially aligned. We have some very, very distinct signature. We know, okay, so gravitational lensing is happening. Okay, so again, so this phenomenon is called the gravitational lensing, is from Einstein's general relativity. So why this is important on the dark matter? The dark matter, we cannot see them, of course, but using this image, using the lensing image, using the lensing data, we can use Einstein's theory and again presume the general relativity is right. We can find the total mass. We work backwards. We can reconstruct the mass distribution of the lensing galaxy, the galaxy in between. Okay, so by using the gravitational lensing, we can find the total mass of the lensing galaxy, and we compare the data we observe, from the X-ray observation, other observation, what the luminous, what the matter we can see, and we also find, okay, so the total mass from the lensing, from the gravity should be bigger than the luminous matter we will see. Okay, again, so the missing matter, the missing mass, we call them dark matter. And so, well, this is, I just for fun, I just pop up a very beautiful, unfortunately, artistic rendering of a lensing of of a black hole. Okay, this is actually from the movie Interstellar. I hope everybody saw the movie, but that's a one of my favorite sci-fi movie. And in this movie, actually, this is a construct. This image is construct, close, using a close enough real data. I mean the real model, and we should, if we get close to black hole and then we have the lensing, we should see an image like this, although the image itself is a rendering. Okay, so that's the gravitational lensing. There's another proof that we have missing matter. And the last proof, so maybe like a smoking gun. Okay, so it's the bullet cluster. Okay, so what we have seen here is that, of course, it's map. So those fancy pinkish, bluish color and the reddish color, and so those are distribution of matter, and in particularly, okay, so this is a distribution of matter that you have a separate the dark matter and then the matter we can see. Okay, so the beautiful bluish color is where you can basically have a data to prove their dark matter is there, and then the pinkish color is where you have observations, probably from X-ray observations. You have the luminous matter, and of course it's an overlay with the actual the distribution of the galaxy. Okay, from this figure, you can clearly see. Okay, so there is a way you can separate the luminous matter, the normal matter we see, and then you have dark matter halo and around the luminous matter, and then you have another distribution of matter again. So the luminous matter at the center, and then the dark matter around the the luminous matter, but they have a relative motion. And from this close encounter, or the I'm going to show that again. Okay. From this encounter or collision of those group of matters, the luminous matter got separated by by this process. Why? Because dark matter, they only interact with gravity, and they will not have friction with each other, so they can pass through each other relatively effortless. Okay, and for luminous matter, and you have the baryonic process, physical process, they have friction, they have other process, they can lose energy, and so they get slowed down. So that in this is from the real observation. You have the luminous matter and the center, and the dark matter get separated and to the edge of the final distribution. Okay, so this is a clear proof that you can have two different matter. They can be at different places, and so since we have so many proof of dark matter, we kind of think, okay, maybe, well, they're true, and they're really there. And so, and I can tell you they account about like, a 20%, around 20% of all the matter and energy in the universe. Okay, so the normal matter is 4 to 5% roughly. So you have, a much more dark matter we don't see than the, the luminous matter, the galaxy, all the stuff we see every day. So what are they? Okay, so can we, we cannot see them. Can we really have some other experiment to actually detect them, to at least figure out what are made of? Okay, so either it's some exhaust object or some elementary particle. Okay, so the first idea is that what, dark matter is not something really weird. Okay, it's just common folks we see every day, but we just don't pay attention. Okay, for example, you have the brown dwarf, the failed star. They don't really emit lots of light, but they have mass, and there are lots of them. And then you have white dwarf, the end product of main sequence star. Okay, maybe they're small, but they are again lots of them. They may be have lots of mass there. And then you have black holes. We don't see black holes. How about we have many mini black holes, black holes are heavy and have a high density, and even for a small size, they can have a larger mass, and then we have lots of them. And so maybe we have that much dark matter, or maybe you have planets. We have lots of wandering planets. This is actually true. And so I think a couple of years ago, a researcher in my alma mater, University of Notre Dame, they used the macro lensing to find lots of, they call orphan planets. They are just wandering around the interstellar space. They don't have host stars, but there are lots of them. But they are not enough. Okay, so let's just look at, okay, so when I talk about micro lensing, how the micro lensing works. Okay, so for the micro lensing, basically similar to the lensing we are discussed like a couple minutes ago, we were discussed a couple minutes ago. And so you have a light from a distant star, and then you have a telescope, and then you have something just pass. So have, a mass is either a mini black hole, you have a brown dwarf, a planet, mass pass between the connection, the line of sight of the star and then the telescope. So when they line up, what will happen is that you have slight brightening of the distant star. Something is there. Okay, so you cannot see the mass, but you can, measure it using the light curve of distant star. Okay, so we do have lots of examples of that. But if you just measure the event rate, how many events we have for this kind of macro lensing phenomenon, either for brown dwarf, white dwarf, black holes, planets, we don't have enough event rate to prove. So they are so common, they are everywhere for this massive compact halo object. They can account for 20% of the mass of the universe. So this is one candidate, but this is a small player. It cannot be the major part of the dark matter. Okay, so then when you come to the other, more exhaustive candidate, we have the neutrinos. Okay, so neutrinos, they are almost massless, particle, and then have weight interaction with other, particles. And the neutrino travel very fast, near the speed of light. And so maybe neutrino has mass. Recently we know neutrino has a mass. Maybe neutrinos has the mass that can be, the dark matter. And there's a problem is that first, the neutrinos is light. Okay, so they need enough mass to account for the dark matter. And then the second, the neutrino is hot. Using the current structure formation theory. Okay, so if you have neutrino and the structure, if you have a cosmology model, you have hot neutrino, they're everywhere. They if they serve as a dark matter, they have the mass of the dark matter, and so they don't really have the same structure we have seen today for the universe. Okay, so but this is still a possibility, and then also they. As later on, you'll see there's they propose another type of neutrino, the massive stereo neutrinos. Okay, so those stereo neutrinos at the beginning they have mass, and later on they have a decay. Okay, so they mean maybe there's fourth generation of neutrino. For those of you who know, okay, so there's 3 generation of neutrinos, and that's a possibility. And then the second candidate is the one, our main candidate is called the weight interacting massive particles, WIMP. Okay, WIMP. WIMP is a kind of weird particle. It's massive. You think it's very heavy, but they are not very heavy. But they have mass. They have interaction with normal particles. But they don't really interact so much. It's weakly interacting. Okay, so how about we have some particles just lurk in the dark, and they have weak interaction with our normal matter, but they have mass, and we don't see the interaction very much. Okay, so that's one of the candidate. Okay, so how do we? So this is a current model. We believe that may be the case. How do we detect those WIMPs? Okay, so the WIMPs, because they are massive, they're traveling relative. Their speed is relatively slow. Okay, so you have the so-called cold dark matter. Okay, cold dark matter, and so the one way to detect those WIMP is using so-called seasonal modulation. Okay, so this is the first one. Actually, they claim a detection, but later on it's just discredit. Okay, at least people don't believe that believe in this discovery that much. Okay, so the theory is that So in our solar system, our sun and the Earth is traveling around, orbiting the center of our galaxy, is and center of galaxy. Okay, so the whole solar system is traveling around the galaxy, but the Earth is also orbiting the sun. Okay, and during a year, at one time, relative to the galaxy, center of the galaxy, the Earth traveling in the same direction as our sun. So the speed versus the galaxy center actually is greater. And the other time, relative to the center of the galaxy, and the Earth is traveling in the opposite direction, as the sun orbiting the center of the galaxy. So the speed relative to the galaxy center actually is slower. Okay, so that's due to the fact Earth orbiting our sun in a year. And so how about we say we presume we have dark matter distributed in our galaxy. Okay, so even in the galactic disk. And if this dark matter will interact with normal matter, because when we're traveling faster relative to the dark matter distributed in the disk, you will have in a given time you have more events. You meet dark matter particle for normal particle, you have more, because you're traveling fast, you have more event detection, you have more chance a normal particle will interact with dark matter particle. This is just like when you're driving faster in the rain, the rain will, the raindrop will hit the windshield faster. I mean, in a given time, more frequently. And so that's the for the Earth traveling in the same direction as our sun. And then other time, when they are traveling in the opposite direction, your car driving slower, you have less raindrop hit your windshield, you have less event that normal matter has interaction with dark matter. Okay, so use this principle. If somehow you can observe in every year, there's sometimes you have you detect some signal that presume be the interaction between the dark matter and then the normal matter, and so you have certain time of the year you have more detection. You have certain time of the year you have lower interaction. That means, okay, so this is called modulation. That means, okay, so we may be traveling in the dark matter distribution in the disk, and we may actually detect something due to this seasonal modulation. Okay, so this is the idea of one of the earliest experiments. It's called the Dhamma Experiment. Okay, so they use I don't really want to go to the detail of the detector and the interaction because that's not my field, but they use some kind of crystals, and then they detect the signal, and then they claim they actually detect this seasonal modulation of the signal. Okay, so but the problem is that nobody repeat their result. If it's true, then anybody else using a similar setup will see the similar signal, but it turns out it's not repeatable. So probably this big news, but probably this is due to some other things, not detection of dark matter. The other most current popular experiment is called the xenon detectors. Okay, so basically you have a big container of xenon, and then you have this xenon detector deep underground. By the way, so all this dark matter, detector, they need to put into the ground, deep into the ground to shield the noise from the other detection. Okay, so in this xenon detector, you have a very pure liquid xenon, and then you have a dark matter particle. They have interaction with the xenon atom, and they have collision in a way, say, and then there's reaction. You can actually emit gamma rays, gamma photon. Okay, emit a photon. Sorry, I should say it's gamma photon, not gamma ray. Okay, so this light, although it's tiny, but we have a chain reaction can get a hugely amplified the light emitted by this collision, and then you can see you have the photo multipliers. We can actually detect those signals. Of course, suppose you have a fixed density of dark matter, and the bigger the detector, the lights, the more likely you can detect this kind of event. Okay, so now they building a bigger and then bigger detectors, and so they haven't have any detection yet. That means, okay, so you can see the this curve. I just want to make a little bit introduction. This this coordinate. Okay, so in the x coordinate, is the WIMP mass. Is the mass. Our candidate is the in the GeV scale. Okay, GeV scale. Okay, so y is in the energy scale because energy is mass. Okay, so divide the GeV by c squared. Basically, you get the mass, and then the y coordinate is cross section. Okay, so if you study a little bit of the high energy physics, you know. Okay, so the cross section means how likely those collision will happen if you have two particle collision. Okay, so bigger cross section means they are easy how a event they actually collect with each other. A small cross section, that means you have a smaller chance they will say in this case dark matter particle will collide with the normal xenon particle. And as you can see, okay, so for those solid lines, okay, so we have built bigger and bigger xenon detectors, xenon 100, xenon 1 ton, and so currently it's xenon 1 ton. Okay, I bring the mouse up, it's xenon 1 ton, and so those solid curve is we have done. Okay, and then those dashed curve is the proposed detectors. Okay, for all the solid curve from the region that is in this case light green, there's no detection. We don't really detect any interaction between the dark matter, the proposed dark matter, and then the xenon atom. And we can build a larger detector, but the problem is that when you have a smaller cross section, you come to the region, you can detect the neutrinos. Okay, you can detect the neutrinos. That's one of the major obstacles the experiment particle physicists facing now. You have the detection of the neutrinos, they call the neutrino flaw. When you have detection of the neutrinos, when you detect something, it's very hard to distinguish whether it's some a new particle, dark matter particle, or you just detect the neutrinos. Okay, so things get much more complicated. So that's the reason. Okay, so the cold dark matter model, the WIMP model now is in parallel because you have detection across the neutrino floor, and if you want to have a further experiment, you need to get a new idea. Otherwise, you get a signal you cannot be sure you're detecting dark matter or detecting neutrinos. Okay, of course there are other candidates. You have the SUSY particle, simple symmetry particle, neutrinos, and so it's combination of couple particles, and axon is a gauge particle or a stereo neutrino. That means the first generation neutrino. All those weird ideas, but again, so those are just a long shot. Then currently we are we're hoping we have some detection of the WIMP. So dark matter particle is really the weak interacting massive particles. Okay, so again, but this experiment is almost approaching the neutrino flaw. We're running the trouble. So maybe we think, okay, so maybe the WIMP is not our candidate, is not dark matter, is not cold. Maybe you try some other idea. Actually, the people are doing some other model. Okay, so the neutrino model, they call this, and then most recently they got the self-interacting dark matter against self-interacting, and then you have the warm dark matter, other series, other candidate for the particle. But again, so the cold dark matter model has been popular for decades, and so although we are running the obstacle whether we can actually detect the particles, but we are not in a time just quickly rule out the cold dark matter particle. Why? Because the cold dark matter model, although we haven't detected actual particle yet, is very successful as a cosmology model. Is very successful to produce the observational clustering property of the universe. Okay, so this is a a power spectrum of the matter in the universe. Okay, so what is a power spectrum? So it's a measurement to measure how the matter going to clustering at a different scale, okay? So as you can see, okay, so from this power spectrum, you have the Planck data, the satellite data on the CMB, you have the SDSS data, the sky survey data, the BOSS, again, another sky survey, and then the dark energy survey, and all those. The last three is the large scale surveys. Okay, so the so for those survey of the galaxy and then the matter, we have a plot of the power spectrum. So for those are the data for with arrow bars with a different color, and then you have this nice smooth dark line here. So that's the prediction of the cold dark matter. You can see, even for an amateur, you can see, okay, so wow, that's a very good model. All the data are just on the line. Okay, so probably that's what's the real model is. And also for the numerical simulation, this is for the Millennium simulation. That is in that is one of the breakthrough in the computer simulation 2005, and we can have a very successful computer simulation to produce the matter clustering, use the cold dark matter model as a start point for computer simulations. And on the first, I don't want to go to too much detail. On the first panel is the 2-point correlation function, and then the last one, the second one is the power spectrum. Both are measuring the clustering property of the matter in the universe. Okay, so again, the computer simulation is also very successful using the cold dark matter model. So if I can say, okay, so the cold dark matter model is the model. We don't really have the detection, but we presume, okay, so some particle still is cold and then can serve as a dark matter. Okay, possible, and but there are also a small scale problem. All these clustering property is on the large scale. So how about for individual galaxies, for individual black holes? And the cold dark matter model is a good model on small scale. It turns out that they have some problem. Okay, so I don't want to go to too much detail, but they have the cusp core problem for the simulation. If you use a simulation to form a galaxy, the core will have a slope of density, but in reality, the galactic center has a fixed amount of fixed density, near a uniform density, and the too big to fail problem, you always have form those big galaxies, and those are those survives. And for the computer simulation, there are smaller ones, but the very small galaxy, but you never see them. And the missing satellite problem, okay, is similar to the too big to fail. And the planets of the satellites, our Milky Way has lots of satellites. They have special orientation, so that means whether our Milky Way is a very special galaxy or not. Okay, and the Bartlett's galaxy, in the simulation, you have lots of a galaxy that does not have a very big bar. Is that the problem? And the sync disk problem. And so you have in the computer simulation, the galaxy disk is very thick. In reality, when you look at sideways Milky Way, you have very thin galaxy. And then the diversity problem, you have lots of different galaxy you cannot form in the simulations. Okay, so why I list so many problems on small scale of the cold dark matter? Because I was actually starting one of the different problem, and the same category is called the high redshift quasar problem in my research at the Penn State University. Okay, so what is the problem? Okay, so the problem is that when you have a high redshift quasar. So what is a quasar? Quasar is a active galactic nuclear. Basically, it's a huge black hole that is accreting mass. Okay, so in the current recent observation, we can find a quasar at a very high redshift 7, and so at the redshift 7, you already have a very huge black hole has a mass of 10 to 9 solar mass, and just after a big bang, like in the millions years of big bang, millions of years, very short in the cosmic time. So how can you have such tremendous black hole and so early so early in the evolution of the universe. Okay, so that seems impossible first for a previous simulation, so very coarse simulation use dark matter only. So what we did at Penn State is that we actually do a zoom in simulation, with very high resolution simulation with the baryonic matter. Okay, so there are two kinds of simulation. Normally, the easiest one you can do is that you just have a dark matter, you form a dark matter halo. So for early type of simulation, you don't even form a galaxy. Why? Because you don't have baryonic matter, you don't have visible matter, you have only dark matter, you just form a halo, and then you turn on the baryonic physics, you can form a galactic disk. In our simulation, we did a very high redshift, very high resolution zoom in simulation to study the early evolution of the black holes. Okay, so I don't want to talk too much about the detail of the simulation. So basically what we did is that we by first do a very large scale simulation. So our simulation in the order size of 1 gigaparsec, we can choose the most massive halo, most massive galaxy, and the redshift z equal to 6. And then we choose our galaxy, or dark matter halo, and then we rerun the simulation, and do a layers of the higher and higher resolution, and then finally we focus on 70 megaparsec, use a very high resolution, and then the very high resolution, and with the baryonic physics, with the physics that deal with the star formation, galaxy formation. What do we actually? This is the actual simulation. So what do we actually find is that, okay, so if we enable the baryonic physics, and if we have highest resolution, and then with all the proper physical recipe for the baryonic physics, you will have a possibility to form a very massive black hole, even at very high redshift. Again, I just want to show you. Okay, so the color here means the temperature. The color means temperature. The circles here are the black holes we formed. We pin our center black hole at the center of the simulation. Okay, so you have in the yellowish color, that means the hot gas due to the feedback by the center black hole. Okay, so and we also compare our black hole mass. Okay, so that is in the order of 9, solar mass, and then we have the bolometric luminosity that's comparable to the one actually observed in the per slide. Okay, so that's our simulation. Okay, so this is, I just want to introduce you something we actually done at Penn State. The other side, okay, so we talk about dark matter, and then the other side of the the other role, the major role of the dark side is the dark energy. Okay, so unfortunately, by just saying dark energy or cosmological constant, we really need some mass. Okay, to just why we have so-called cosmological constant or dark energy. So let's just use like 5 minutes to actually go through some very fundamental setup for the modern cosmology in order to understand why we have dark energy. Okay, so first of all, in the modern cosmology, we have an assumption that the universe is isotropic, is homogeneous everywhere. Okay, so that means if you look at a certain part of the universe, okay, so every direction is the same and everywhere is the same statistically. Okay, so that's our assumption. Okay, so universe basically is same everywhere. But you may be saying that's not the case. Here we have Earth, other places you have Moon, you have other planet systems. So why is the same everywhere? That's small scale. Now we're talking about the larger scale. Okay, so for larger scale, the universe is isotropic and homogeneous. Okay, so you have a mathematic way to describe this kind of space-time. Okay, so that's the FRW metric. Friedman, Robertson, Walker metric. Okay, so I don't want to go through too much detail, but this just tells you, okay, so you can separate time and then the space, and then the size of the universe can be described by the scale factor. Look at the equation. Okay, so A is called the scale factor, A squared T. Okay, so that's our size of the universe, universe. The scale factor is not absolute size, it's relative size. Okay, and then of course, in order to study the universe, we start gravity, we need the Einstein equation. Okay, so this is the Einstein equation. Okay, so Einstein equation is connect space-time to energy. Okay, so in this equation, on the left side is the Ricci tensor, and then the is R mu Way is the Ricci tensor, R to Ricci scalar, G mu Way is the metric we have defined here. So the left side is the space property, the right side is the energy property. Okay, and again, so we are not doing general relativity, but anyway, combine those two, you have a equation called the Friedman equation that is govern the size evolution, the scale evolution of the universe. So H is called Hubble parameter, is the A dot means the time derivative of the size of the universe, divided by A, and then square, and then the right side is the 8 pi G. G is just gravitational constant that divided by 3, and rho is the density of the universe, minus kappa is the geometry of the universe. Just for now, we just believe the kappa is 0, so our universe is flat, divided by A squared. Okay, so again, I don't want to go to too much of the math, and eventually, if you separate the energy, we have in the universe, matter has energy, and sunlight radiation has energy, curvature has energy, vacuum has energy. You can rewrite the Friedman equation, the last equation this page, into H squared equals to H naught squared, that's the Hubble parameter, times omega, that's the energy, that's the energy density parameter, omega. Omega is representing what kind of energy you have. What is the magnitude of omega is proportional to energy density of each component, matter, radiation, or a vacuum. Okay, so anyway, so the size of the universe, that's H squared, related to H squared, is really depending on the different energy component of the universe. Okay, so why this matters? This matters because we know, okay, so by the CMB observation, we know the omega, the total energy density, is normalized to 1. Okay, so it basically say it's not normalized, just say it's 1. Okay, so that means our universe is so-called flat. Remember, okay, so the omega can contain, omega total is 1, omega contain different energy property, okay, different energy density, matter, radiation, or other type of energy. Okay, so we know from the CMB, from the cosmic macro background, from the COBE, WMAP, Planck data, we know the universe has energy parameter equals to 1. The total energy of the universe we can treat as 1. Okay, and so that's all we know from the CMB. Okay, so the recent breakthrough is from 1997, 1998. We have a better idea than just say the omega total is 1. Okay, omega total is 1. You don't know what fraction of the matter, what fraction of the energy radiation is. But there's a recent, not too recent, 20 years ago, I mean, in a cosmological scale, a cosmic scale is recent. Okay, so you have a very, 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 very significant discovery is that using type 1a supernova, we can actually know, okay, so what fraction is matter, what fraction is radiation, what fraction is so-called the vacuum energy over cosmological constant. So what we have is that here is type 1a supernova. If you know the type 1a supernova, this is a special type of supernova. You have a core collapse supernova that can be a massive star and then collapse to form a supernova. And you have another type of supernova that is white dwarf and a companion star, and the white dwarf keep getting matter from the companion star, and until it's reached a fixed mass, the Chandra scale limit is a couple of solar mass, and it will completely blow apart. And so that mass is fixed, is a fixed amount of mass, and in the multiple of the solar mass, and that mass is fixed no matter it's now or like billions of years earlier. The physics is the same. Okay, so we presume, okay, so the type 1a supernova just blow up in the same way. Okay, so this is theory, and in 1998, finally they figure out a way from the observational side. They can figure out a way, use light curve to actually find the intrinsic brightness or magnitude of a distant supernova. Again, since the type 1a supernova always is a result of a blow up of fixed mass, fixed amount of mass, we presume the energy release in that process is very similar or same. So in 1997, 1998, finally they can figure out a way to find out the intrinsic brightness, or they can calibrate the absolute magnitude of the type 1a supernova, when the supernova went off in distant galaxy. So they can figure out the absolute magnitude. Of course, they know the apparent magnitude. They can measure the brightness of the supernova, and then, for those of you familiar with this relationship. Okay, so last equation. So the distance. So you know the distance of the supernova because you have a standard called a Stein candle, a object with fixed amount of the luminosity. That their the luminosity, the apparent brightness. So their absolute magnitude, the luminosity, and then the apparent magnitude. You can figure out their distance. That's the DL, that luminosity distance. So why this is important? The luminosity distance, using our using our cosmology model, is closely related to the density of each component of the universe. Okay, so the second in the second line of the equation, the E, that's energy, can be a function of different components. They involve in different ways, and so, using the supernova data, we find, okay, so if the total energy density of the universe is 1, matter, including dark matter and normal matter, only 30%. The 70% is the energy we don't know. We know it's there, but we don't know what kind of energy it's from. It's not radiation for sure. It's some kind of energy we don't know. Okay, so that's the idea of the dark energy, or the cosmological constant. Okay, so that's the 1997 data, 1998 data, and so how about now? Okay, 20 years later. So are we know more about dark energy? Okay, so it's kind of, we shrink the error bar, and we still trapped in a way. Say the dark energy is about 70%. Is about 70% of the energy in the universe. And then on the left, on the right, you can see that's the 1998 data. Now we shrink this range to a smaller one, but the center of that curve, that means the pair of the matter density and the dark energy density still is like 70%, matter 30%, the dark energy is 70%. Okay. And so what is dark energy? Okay, so there's lots of theory. And the most popular one, maybe even the right theory, is that we have cosmological constant. Vacuum has energy. The emptiness has energy. That's just what it is. That's the nature. Okay, so we have so-called cosmological constant. Here is a 2017 paper, just say, give us some idea. Okay, so again, I just want to explain a little bit. Omega m is the matter density. Omega, the W is the the so-called the equation of state parameter. If it's -1, that means this is constant. Okay, so the second figure, the x coordinate is W0 is, and then that means -1. That means the is constant, and WA is changing of the W0, changing is almost 0. Okay, so that means. Okay, so we do have the cosmological constant, at least from the data. So are we done? Okay, so just says, okay, so we have a cosmological constant. So we have an energy that is from vacuum, that's the dark energy. Are we done now? And so not so really. Okay, so there's some problem. Why? Okay, so the first problem is that, okay, so how do you know the magnitude of vacuum energy is the energy we have now? We have current. We have current high energy theory. We have lots of brilliant high energy physicists, and they have lots of theory, and none of the theory predict the correct vacuum energy. Okay, so they predict much larger vacuum energy. Okay, so much larger cosmological constant. So no current theory can explain the magnitude of the cosmological constant. And then we have the problem is that, okay, so look at the figure on the bottom. So this just showed you the age of the universe, and then the evolution of different form energy, matter density, radiation density, and the dark energy. Okay, so the energy density for different form of energy. Okay, matter, radiation, and dark energy. It turns out, roughly now at the current moment, we have a comparable matter density and then the dark matter energy density and then the dark energy density. Why is that? Okay, so previously, say at the beginning of the universe, dark energy density is almost nothing compared to the matter density and the radiation density. Okay, so why just now we have a comparable, roughly same order of magnitude, dark energy density and then the matter density? Is that really mean something? Does that really mean something? And we don't know. Okay, so but it's something suspicious, something maybe just telling you something that dark energy may be from the matter density. Okay, so another way to explain that. Okay, so why we have such a small dark energy density or a vacuum energy density is that we are living in this universe. Only this creature, only the living things in this universe can observe this kind of dark energy density. Okay, so this basically you kick the ball further away. You just want to offer you a comfort explanation. It's called isotropic principle, and frankly, so I think this is just kick the ball further away, and so just say let's just believe that's the case. Okay, so. Of course, this cosmological constant theory, seems most likely is true, but it just does not give us convincing explanation. So there are other, explanation of the energy density. You have the quintessence model. That means, the energy density is changing. Fountain energy. That means eventually this energy will rip everything apart. Extra dimension. Okay, so this comes from extra dimension, and dark energy somehow is the other side of dark matter. And you have the so-called book viscosity. So basically, we have in a higher dimension, two dimensions just passing each other produce this kind of energy. And then you have the model for the general relativity. Actually, Einstein is not right. Okay, so the general relativity is not valid on a very large scale, on the cosmological scale. And then the reason I list this is that I did a some kind of like a brain work on to explain the dark energy by another kind of explanation. Is that what, our universe on a small scale is not homogeneous and isotropic. In our solar system, majority space is empty, and then you have the planets. Okay, so that's not homogeneous. Okay, so what do we do? Okay, so of course, on a small scale, we don't have a the homogeneous and an isotropic universe, because the density just are off by a large of the magnitude. Okay, so in order to study whether this small scale inhomogeneity can create observation to observe the dark and to observe the apparent dark energy or cosmological constant, we need much more mass. Okay, I don't really want to. We're almost out of time. I really don't want to go to too much detail, but I just want to spend maybe 2 minutes to explain what is the logical way to do it. Okay, so first, in order to describe a inhomogeneous universe, we lose the luxury to treat the space as a flat, as a very flat fabric. Okay, and we must treat space as with all the with all the deformation in a way say caused by the energy. Okay, so in order to do this, we use a new kind of general metric for the space-time. It's called ADM 3+1 formalism. Basically, we have a much general metric to describe the space-time in a more general matter distribution. Okay, so we have the metric. And of course, there's a way to explain. Okay, so how we construct this metric, and then we need to figure out the expansion, the cosmological constant, and the matter density really relate to the size of the universe. Again, the scale factor A, the Hubble constant, relate to the expansion of the size of the universe. We need to define locally. Okay, if we divide the universe into a small domain, what is the volume of that domain? Okay, the volume that the domain can be constructed use the previous metric. Okay, so now we have a new definition of the size of a certain patch of the universe using the new metric, and then we use the Einstein equation to get a new Friedmann equation on a small scale, on a small patch of the universe. This patch may just contain nothing. This patch may contain a rich cluster of galaxies. And so this is called the domain. So now everything with a lower subscript domain. So that means domain Hubble parameter, domain scale factor on a certain domain. Okay, so now we have the local domain, and we can use the Einstein equation to relate the size of the local domain to the energy inside, So the matter inside, the energy inside. Okay, so again, and then now we want to figure out how do we actually calculate this size of the local domain of the universe. It turns out, okay, so we can simplify our expression to use some even more simple metric to write a space-time into a perturbation. Okay, so we cannot study black hole in what's inside black hole because that's not something we can do, but we can evaluate the space outside black hole, near the galactic center, near the planet, near the star. So we use a cosmic perturbation theory to rewrite metric as a flat metric, but perturbate by a small perturbation generated by the matter distribution. And so what are the perturbation are? The perturbation actually is the using the cosmic perturbations theory, you can prove the perturbation of the metric is actually from the gravity is from the gravitational potential generated by matter. Okay, so in other ways, say we are using our matter distribution that generated the gravitational potential actually to describe our current our local patch volume. This is messy expression. We can rewrite the new size of the domain and the new size of the new energy density using our gravitational potential. Okay, so again, so that's lots of math, but eventually we say, okay, so the reason we are interested in this is that we think the local matter, the distribution matter will cause the perturbation of our space-time when we have matter inside to generate the gravitational potential. So in this case, we have a plot that shows you, okay, so when structure form in the universe, we have the gravitational potential that will grow along the structural formation. But in this case, you can see the peak. That's near the center of the galaxy cluster. Okay, we use that one as a correction to a flat space-time. Okay, so how big those correction will be? How big this correction will be? It turns out, okay, so that's not very huge, because again, we are not talking about black holes. So the average correction should be in the order of 10 to the negative 5, maybe 10 to the negative 4, because again, so we are not starting the space between the inside the black hole. We are starting, the space near the the planet stars or near the galactic center. So even there's a correction, that's not a huge correction. Okay, so anyway, so we got this the gravitational potential information from our computer simulations, because we kind of have a realistic computer simulations. We calculate that. It turns out that's probably not enough to just explain why we observed our dark energy and cosmological constant from the observation. This local change in the volume, the size of the universe, does not account for the vast bigger change and the size of the universe, the acceleration, the size of the universe due to the current theory, that current observation. That's the dark energy, that's the cosmological constant. So maybe, although, like I said, this is a brief but unsuccessful explanation, but maybe we have other explanations. But for now, we just believe, okay, so the current cosmological constant cold dark matter model is our current model. It's called the lambda CDR model, and so it's still the best model. And for the true nature of dark matter, dark energy, we really need to do more work. Okay, dark matter, we can build detectors, maybe more. And for dark energy, we need some very new idea, just figure out what is the 70% made of. And the numerical simulation maybe can offer some hint on this possible explanation of the dark matter and dark energy. Okay, thank you for your patience. I a little bit over time, but thank you for your patience. And now I'm ready for the questions.
Thank you, Xinghai. I have a question, just as it relates to the audience here, so they'll know, what is the cosmological constant, okay, first off, and how does that relate to dark energy, okay?
Okay, so let's just back up a few slides, okay. So we need to get back to Siri here. Okay, in the last line, now I really need to go through some math now. Okay, so in the last line is the Friedman equation, right, in a new form. Okay, so the H, remember what is H? H is A dot over A. So what is A? A is the scale factor of the universe. That's the relative size. By the way, for the current universe, A equals 1, okay, just by definition, A equals 1. So that means, the scale factor of the current universe is 1, okay? And then, of course, early on is smaller, okay? So A is the relative size of the universe. And then the Hubble, the H square is defined by A dot over A. By A dot means the time evolution of the A and over A square, okay? So that's really containing information of the size of the universe. So that piece equals to 8 pi g is the gravitational constant over 3, and then sigma rho I. Okay, so this rho I is the actual energy density of each component. Okay, matter, and then the radiation, and then the curvature, and then different forms. Okay, so. But now let's just do some, again, additional math. The last term, we rewrite this energy density into a new form. we know, okay, so the current density of the universe is, we can define as the critical density. So what is the critical density? The critical density is basically say, okay, you know what, 3h squared, so h squared is 8 pi, h squared is 3 pi, is 8 pi g over 3, and then this term, that's all the energy density. That's called the critical density. Okay, so we define the critical density as 3h squared over 8 pi g. Now you can define a parameter omega. Omega is defined as, okay, so each component's energy density versus the critical density. Basically, you normalize it. One with the critical density, and then other just fractions. Okay, others fractions. So basically, say the total in this way, you define the critical density as 1. So the omega I parameter is only such a percent, how many percentage energy you have. Okay, so in this critical energy budget, in the total budget. Okay, so once we have this, so of course, the total omega, the omega now is the percentage is 1. Okay, so the universe is critical, and we know universe is flat, so there's no curvature in the space. So all the energy add up will make universe flat, make the critical density, make the universe flat. Okay, so omega naught is 1. In this picture, omega naught is 1. So that means our universe from the CMB, from the cosmic wave background, we know that omega, all the density, matter density, the radiation density, the dark, the vacuum density, they add up as one. So what this means, let's back to the previous slides. In the previous slides, we said h squared, a dot over a equals this stuff, and then minus kappa over a squared. That means this kappa is the describe the curvature. So that means this term. If we close this equation without kappa, that means kappa is 0. This kappa means 0. Okay, so that means, okay, so the critical, if we define the critical density, and we did have a critical density, so we don't have a curvature in the previous Friedman equation, so that means our universe is flat. That means all the energy density except the curvature density. So we don't have a curvature, we're flat. So all the density, that is the matter density, the radiation density, all the other density add up as 100% as 1. Okay, so then why this matter to the, we call it the dark energy, is that, okay, so now that, you have the supernova explosion, type 1 supernova explosion, you can have a formula that fit into the luminosity distance. So the difference between the apparent magnitude and the absolute magnitude is related to the luminosity distance. Just basically like you are bulb that further away is dimmer. So by the fact how much is dim, you know the distance. In this case, you have this information in the last equation, and this luminosity distance is really a function. Is omega. Omega, remember, is the relative percentage of the total density unit, total energy density of the universe. Okay, using the supernova data, you kind of know, okay, so the omega matter is the matter density is 30%, omega lambda, the dark energy density percent is 70. Dark energy density is 70%. Actually, we don't know that. So let me say this. Using the fact the total density omega must be 1, and then we know matter density is 30%, and we don't know what is the rest of the energy density. Okay, so we don't know. We know matter is 30%. We know total is 1 by the CMB data. So what about the rest of 70%? So what are they? Okay, so is that radiation? Is that vacuum density or cosmological constant? So what the supernova team, what the High Z team, and then the supernova cosmology project, what they do is that they presume this is a constant. That means this energy 70%, this energy density is a constant. It does not vary with time. Okay, so in this model, because as you can see in the previous slides, all those energy density is a function of z. Z means time. Okay, so the Ez is a omega parameter times z, a function of z. That's time. So we know the matter density, as volume expand, matter decrease as divided by volume. Okay, so as the scale factor cube. But we can presume in this case, if the energy density does not depend on the redshift. So if it's not changing with the time, we have this model, we can fit our data better. That means, okay, so for this supernova discovery of the dark energy, they just presume we have 70% of energy does not vary with time. So that's how you get the name of the cosmological constant, because we presume it's not changing with the time, the energy density. It has no z dependence. The matter density has z dependence, will be diluted by the cube of the size of the universe. The radiation will be diluted by the fourth order of the size of the universe. But omega lambda will not dilute because it has no z, no redshift dependence, no time dependence. Okay, so that's why you call it cosmological constant. So this is more native way say it, but by say dark energy, just except we don't know what it is, but we know it's constant in a way say.
Thank you.
Sorry, I maybe just involve too much math, but I really hope some can just at least I think have a better understanding. Because previously I may just skip too much math on this perspective.
Okay, so are there other questions out there? There's a lot to unpack there. I know we basically took a trip across all of cosmology, covering a lot of themes there. So any other questions from the group? Maybe on just certain elements? Go ahead, Bobby.
Yeah, Bobby, did you have a question?
Can't hear you, Bobby. Still can't hear you. I can see you talking, but I can't hear you. Is your mic muted? No.
Nope.
Can you type it? Just go into chat and type your question. Okay. Anyone else?
Mm-hmm. Yeah. Yes. Okay. So what is quintessence model? So basically in the quintessence model, and you have, let me go to that slide. So you have, basically you're having dark energy, but the dark energy is not a cosmological constant. It's not a cosmological constant. You can rewrite dark energy form as a function of time of some kind of field, either a scalar field. I don't know whether you're familiar. In high energy, field has energy. Okay, so you can either the Hamiltonian or some energy from the scalar field or other type of field. That field have a certain form, and the energy density of that field can have time variation, but it will be very slow changing across the cosmic time. The energy of those, like for example, the scalar field can have a magnitude of dark energy, but it is not an absolute constant. You can have a very slow changing over the time. Okay, so that's basically what the quintessence model is. You can read some reference. They have a different kind of field, different kind of mathematical form, different Hamiltonian of the field, and can have a alternate explanation. Okay, why we have this kind of energy density we observed. Yeah, but I hope this is the quintessence you were reading about. But that's at least for the dark energy. This is what is talking about for the quintessence field model.
Are you trying to map out the dark energy in the universe?
Can you repeat that question again? I'm not sure whether I understand the question.
Well, we have clusters of galaxies.
Yeah.
And showing your fabric of the universe on your pictures there, you have big expanses of nothing. There's no galaxies or anything.
Yes.
Oh, it's everything is so complicated. And also, did this lead to the Hubble constant not being constant? It's accelerating expansion of the universe.
I think you are actually talking about one of the model. Actually, lots of people publish a paper on this. It's called so how about called LTB model, or how about we are at the center of the void? Okay, so think about look at those simulations. They from the very homogeneous universe, and then you form huge void, and then all those matter just moving away from us because we are at the center of the void. How about we are at a special location, we're just at the center of the huge void, and then we observe everything just moving away from us? Is it possible? If you construct a theoretical model, using very special model, this can explain dark energy for sure. But the problem is that there's no proof we are so special in the universe. We are in the huge void, at the center of the huge void. Look at the like Sloan digital sky survey or other sky survey. We are our place in the universe. I think is pretty common, pretty general place. We are not at the center of a huge wall, so that's the problem. So that's also one of the driver for me. Actually, in my study, I use a very general computer simulation to see whether those clustering of matter can make a difference. If we are not at a very special place, we just at a random place. And we run the simulation, we find out, okay, so what, for a general place, not at the a center of the void, we don't have a huge impact by the the clustering of matter, by the the structure formation. Okay, so that's the conclusion.
What about, could it be possible that we might go back in time to Hall, where he, talks about the constant matter in the universe, that if we got the Hubble constant, we're accelerating in expansion, but matter is being replaced as we're expanding the universe?
You mean go back when the time just flow backwards? What we will see?
No. I'm just mean back in history that Hall, came up with the as opposed to the I'm sorry, I can't explain. That's a long time ago. Okay, what about when a supernova explodes? We have shock waves. We have shock waves in gravitational waves? traveling constant. What would be their cause? I think, don't we have where dark matter becomes visible when a shock wave hits the dark matter?
You mean the shock wave, the supernova can expel dark matter?
Yes.
Again, I'm not experimental physicist, but I think that may be something we can look at when the problem with the supernova is they're all very, very far away. Okay, so I don't think you can have detailed study the shock of the supernova. You need some. You need some. Also, if you have dark matter, the shock of the supernova is rather a small patch of the sky. I don't think you can detect a huge signal from this kind of small scale, and that supernova is rather farther away. But one idea is that similar to this one is for the galaxy collision. When two galaxies collide each other, presume they are dark matter. Also at the center of the galaxy, they also have some kind of process. Whether you can detect something, the similar idea, whether you can detect something or this kind of galaxy merger or interaction with dark matter. Okay, so I think there's something similar for that.
A friend of mine, his name John Rather, he'd be rather ancient right now. He discovered some kind of shock wave or something like that in the Orion nebulas, and it may have helped produce protoplanets there. So that's one reason I was thinking about something.
Okay, yeah, that means maybe something new, but I didn't really read the paper, so I don't have really any comment on that. Yeah.
Yes.
So I have a question. Are you familiar with baryonic acoustic emissions?
Yeah. That's part of the. So by the way, so if you were talking about that, one of the survey I mentioned. Let me see. There's one slide that actually show one of the survey there. Okay.
BAO right there. Okay.
Yeah. BAO is the from their baryonic. That means baryonic acoustic oscillation, and there's a couple of data. CMB just shows the universe is flat, and then the SN1A means type 1A supernova. And then the BAO means baryonic acoustic oscillation. Also, one of the survey, I think I see one of the survey. Where is it? Okay, so here. So the SDSS is a Sloan-Digital Sky Survey, and you probably all knew that. And then the BOSS survey. The BOSS survey actually is a survey study they kind of studied baryon acoustic oscillation. And then the DES survey, so it's dark energy survey. They also study not essentially just on the baryonic acoustic oscillation, but it's also a large scale structure survey. Okay, so that's the idea. I don't really have a slides to show you. I did have a slide some time ago, but there's a couple of slides I can show you about the baryonic acoustic oscillation. But so this is one of the signature. This is one of the measurement they are doing to study dark energy. And if you are familiar with this, they say, okay, so if you do a power spectrum or to measure the clustering, measuring the clustering of the galaxy or structures, you will find at about 100 megaparsec scale. 100 megaparsec scale, and you will find a peak of the clustering. That's because from the early universe, and then everything spanned, and then to now, the size of that peak was 100 megaparsec. And so you can use this size changing with time. You can use the size of this peak the size of this clustering to measure the size of the universe. Okay, so that's the idea. And I'm not sure, unfortunately, I don't have any slides to show you here. I can talk much more than that.
But yeah, okay, so if I understand this correctly, back when the universe was more compressed and it was essentially being influenced by, the baryonic matter was compressed so that if a wave propagated through it,
is a sound wave. It's sound wave.
Imprinted
sound wave matter.
Of both baryonic matter, but also dark matter?
For the dark matter, again, so we don't even know the nature of dark matter. So I'll just, on the cautious side, I'll just say I think it may be dark matter, but just on the baryonic matter. Okay, so that's called the baryonic acoustic oscillation, not for dark matter.
Okay. All right, does anyone else have any questions? Okay, if nothing else, I think we're going to wrap it up. I'd like to say thank you to Dr. Zhao for the presentation. I'm sure I'll be going over this for the next several weeks, trying to get a better handle on it, and you've given me a lot of new things to look into, so I appreciate that. I didn't understand everything you said, but that's good, because that means that I've got a lot of stuff that I can look into. So thank you very much for the time. And this presentation, I assume, is going to be on our YouTube page. Is that correct, Matt? So we can go back and refer to it. And I'm going to have to chase down a lot of the terms here that I wasn't familiar with, but thank you again very much. And any other comments?
Thank you, Xinghai, for your time.
Thank you all for coming to my talk, and I really appreciate the opportunity to present my talk at the BIS.